Welcome, ladies and gentlemen, and sorry about the late release of this. I totally forgot being on vacation that I had to work tonight, and I do truly apologize. We're going to skip a little bit and go to experiment 45 tonight. Experiment 45 is very, very, very short in the actual lab portion, and then we'll have a second portion of our analysis. You're going to have to do a melting point and a titration tonight, so hopefully you can retool your titration skills again. Our scenario tonight in experiment 45 is that someone, Willie Hackett is the guy's name, thought he could take the chemical maleic anhydride, which maleic anhydride is used in all kind of production all over the world. It's a very popular compound. It's very cheap, abundant, um, and it turns out that you can just essentially, under a certain catalyst with oxygen, you can take benzene. Both of those are pretty prevalent. Oxygen from the air is all you need. So basically, if we oxidize benzene, which is just, of course, just C6H6, you can create this compound. And that mechanism is a very detailed mechanism on how to do that, but it's done all the time. And it turns out that this chemical is actually used to make a solvent, tetrahydrofuran, which is very commonly used. We've not used tetrahydrofuran yet, or maybe we did use it once, but it is a very common solvent used. Plus, it turns out this chemical, it turns out that it's in a lot of dyes, surface coatings, pharmaceuticals, lubricants, agricultural chemicals, polyester resins. So it's a very popular chemical, can be used for a lot of things. But so Mr. Hackett thought that he could easily come up with a cheap way that he was going to use for his research to create tetrahydrofuran, which tetrahydrofuran very simply would be, we just knock off these two oxygen groups here, and we just have the ring with a single bond in it here, and leaving one oxygen. I don't have one for that. We could look it up real quick. You can see it is the double bonds gone, and the double bonded oxygens are gone. So very common chemical to use, and that was what Willie was going to do with his program. And he thought, real simply, if we go back to this one, he thought, well, I could just hydrogenate these at these. He thought it would be very easy to do, and he was going to do that by taking zinc and hydrochloric acid. So he didn't have to use dangerous hydrogen gas, and zinc and hydrochloric acid would produce hydrogen gas in solution. So now he's got a strong acid and zinc. So remember those. And what he thought was that the hydrogen then would go ahead and hydrogenate hydrogenate these sites, eliminating the oxygens, and hydrogenate this site on the double bond, and that he could create the tetrahydrofuran. Tetrahydrofuran is a liquid, low boiling point liquid. When Willie did his experiment, he obtained a white solid. Upon further analysis, preliminary reports said that he had produced a carboxylic acid. So the question is, in the process of taking, which I know you're going to be able to go out on the internet and look up what happens if you take maleic anhydride and you add hydrochloric acid and zinc, you'll be able to see what it makes. So you could probably find that out before you got to lab. But our job is to determine tonight, what actual carboxylic acid did he make? Does it break these bonds so that you create, typically a lot of times when you have anhydrides, really common reaction. I'm trying to think if I have any of the common anhydride reactions, but typically what it'll make is 2 units me say that again, 2 units of carboxylic acid. So we would expect this thing to break in such a way that we would get 2 molecules of that. So our job tonight is then to determine what carboxylic acid we made. We're going to be able to get the melting point. There's a list of carboxylic acids in the back of the book, and you'll be able to get a close melting point range. Of course, it turns out that when we make the chemical tonight, when we produce whatever we make, it needs no further refining after you crystallize it. And once you crystallize it, it will not need to have any other purity test done. So as long as you just get that fairly dry, you should be able to do your melting point and get a fairly close melting point. But then that's not all. What we're going to have to do at that point is we're going to have to do a titration. And the titration is going to give us what are called the equivalents of hydrogen. And based upon that, we should be able to determine which one of the choices near our melting point would be ours. So we have to talk just a moment about that a little bit. But so I don't know if you remember back to equivalent weights, or if you've done anything with that, if you've had some chemistry in terms of, gosh, I'm blanking on the name of it, analytical chemistry. One of the things you do is you talk about equivalent weights. And so what we're going to end up getting is probably more like an empirical formula tonight. So just as a quick reminder on this, for example, HCl has 1 equivalent of hydrogen on it, whereas something like H2SO4 has 2 equivalents of hydrogen. So if you put in, for example, if you put in a strong base, 1 mole of base can neutralize 1 mole of this acid, whereas it would take, if I used 1 mole of base here, I could only get rid of a half a mole of this because of the 2 H's. So if we do a neutralization reaction with these, that's what's going to happen. So what we'll do is we'll do a quick titration. Calculation shown on page 391 of an example titration, but if you'll remember, molarity of acid times volume of acid equals molarity of base times volume of base, or moles of acid equal moles of base whenever you titrate. Well, in our case, our acid is going to be a solid, so we're going to be able to find the moles of acid. It's going to equal the molarity of the base we use and the volume of the base we use. You will be given this. So you'll weigh out a sample of this acid. You'll know the mass of this. And then over here, what you'll be able to do is you'll know the volume. Well, that'll give you the moles. So over here, you're going to know that moles equals, over on this side, whenever you think about moles, we know that that's going to be mass divided by the molar mass. So in our case, once we get this number of moles, we can plug that in here. We'll know this, rearranging, if we have mass divided by moles, that's going to give us the molar mass in equivalence. Now, the molar mass in equivalence means it's going to be some multiple of the real molar mass. So you're going to have a list of a bunch of acids near your boiling point. And what you're going to do is, let's just say, for example, this comes out 90. Then your material would have to be some multiple of this. So it's either going to be exactly 90 grams per mole, or it's going to be 180 grams per mole, or it's going to be 270 grams per mole. This being 1 equivalent, 2 equivalents, 3 equivalents. So your job, real simply, will be just to look for that in terms of once you do your titration, and you'll know the molarity of this, and then you'll be able to do that. So I'm going to stop this and then move into the second video to give you some quick summaries, and we'll go from there.